These are the notes for Objective 4, Graphing Trigonometric Functions. Now that we're familiar with evaluating trig functions, it's time to take those values and plot them on a graph. You're probably used to a typical Cartesian coordinate plane for graphing, where you might be labeling the x-axis 1 through 5, the y-axis 1 through 5, and this type of scale works really well when graphing linear functions, quadratic functions, exponential functions, or any other functions where the input values tend to be integers. However, when we're graphing a trigonometric function, we have to think about the fact that we're trying to graph angles. And as far as we know, the domain for angles is 0 to 360 degrees or 0 to 2 pi radians. So as we graph trigonometric functions, you see that we use a different set of coordinate axes in order to get an accurate picture. So what does graphing it look like? In order to graph a function, you need a set of input and output values. Let's make a table of the first quadrant for sine. Thinking of the unit circle, in the first quadrant, what are the angles that we have? We have 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So let's just graph these values. The domain, when graphing a trig function, is the angle. The range is going to be the coordinate of the trig function that we're graphing. In this example, that means sine. So what are the sine values at each of these points? Well, this ordered pair has a value of 0 for sine. This ordered pair has a value of 1/2 for sine. This ordered pair has a value of rad 2 over 2 for sine. This ordered pair has a value of rad 3 over 2 for sine. And this ordered pair has a value of 1 for sine. So with this in place, we can actually graph the first quadrant or first turn of our sine function. Now, when we graph a trig function, instead of doing our standard Cartesian plane, we're going to modify it to graph angles. You'll see a longer x-axis for the domain and a normal or shorter y-axis for the range. Well, taking a look at the values I want to graph, my range goes from 0 to 1, and my domain goes from 0 to 90 degrees. Remember, domain are all of the x values, and range are all of the y values. With that in mind, I need to scale the x and y axis in a way that will allow me to graph all of these points. Since I'm only going from 0 to 1, I'm going to put 1 at the top of my y-axis and -1 at the bottom. Halfway in between is 0.5. And then I'm not going to label these, but I'm going to go ahead and put tick marks for the 1/4 values. Now my domain, again, this is only the first quadrant here, 0 to 90 degrees. I eventually want to be able to graph the entire sine function. So I'm going to label this graph knowing that this is only 1/4 of the way there. Halfway is going to be 180 degrees. The full rotation will be 360 degrees, 90 degrees, and 270 degrees. When you are labeling an x-axis, you must count by equal amounts. Looking at this domain, you'll see a jump of 30, 15, 15, and 30, which means counting by 15 degrees is going to be the only way I can get an accurate scale. Here's 45, 135, 225, and 315. Now with that in mind, knowing I'm counting by 15s, we want to think about how many or how close 30 degrees should be to 45. 15 degrees, 30 degrees, 60 degrees, 75 degrees. And I'm going to continue putting 2 tick marks in between each of these values for each of the 15-degree marks. Notice I'm not labeling them. I'm just marking them so that I can try to draw as accurate of a picture as possible. Now, let's actually graph this curve. Starting with 0, 0, sine is distinct from cosine because it starts at the origin. I need to graph 30 degrees, 1/2. Well, 1/2 is exactly 0.5, so my first point goes here. 45 degrees graphs as rad 2 over 2. Well, rad 2 over 2 is approximately 0.7. So I want to go to 45, about 0.7, which will be just under 0.75. And then rad 3 over 2, which is approximately 0.9. 60 degrees, 0.9 is closer to 1. Well, what happens at 90 degrees? Now keep in mind I'm going to take a little jump on my x-axis. 90 degrees, I get to exactly 1. Connect your dots in a continuous curve. This is the first fourth of the sine function. We're going to repeat this process to finish our sine curve. Now, I'm not going to show the unit circle anymore, but if you have one out or have one, you should be looking at the unit circle to help me complete the rest of this table. After 90 degrees on the unit circle, we see that sine takes on the following values: 120, 135, 150, 180. At 120 degrees, sine is rad 3 over 2. At 135 degrees, sine is rad 2 over 2. At 150 degrees, sine is 1/2. And 180 degrees, sine is back to 0. Let's graph these points. We remember from before that this is about 0.9, so we want to try and get a symmetric point here. We know that rad 2 over 2 is about 0.7, which is here. And we know that 1/2 is exactly 0.5. So by the time you get to 150 degrees, you want to be back at 1/2. Big jump to 180 degrees at 0. And now we've completed half of a sine curve. Repeat this process for the remaining 2 quadrants. And here we've completed 1 full revolution of the sine curve. Now this is considered 1 period of the sine function. A period is the length of time that it takes to complete 1 full revolution of the curve. However, we know that when we're dealing with circles, the function doesn't stop at 360 degrees. What's going to happen if we continue our domain into the next revolution? Well, let's just take a peek at the values obtained going past 360, but still dealing with angles coterminal to those on the unit circle. After 360 degrees, we would have 390 degrees. After 390 degrees, we would have 405, then 420, 450, and so on. If you think about these as coterminal, 390 degrees is equal to what angle on the unit circle? If you were thinking 30 degrees, you are correct. Similar process. We're just subtracting 1 full revolution from each of these angles. And so the output, or the range, of 390 degrees is 1/2. The output or range for 45 degrees or 405 degrees is rad 2 over 2, rad 3 over 2, and 1. What does that look like? After we get to the end of the sine function and complete one full revolution, we will begin to repeat the values already obtained. This is because sine is considered a periodic function. Periodic functions repeat a set range of values over a certain time interval. In this example, that time interval or period is 360 degrees. However, as we practice graphing functions, we're going to see that this interval will change. So, in summary, sine is a periodic function. Its value range from 0 to 1 to 0 to -1 and back to 0 before it repeats itself for another revolution. I'm going to erase this table on the side and just lay down some key information when you're graphing a sine function. F of x equals sine x. There's a few things to note. One, when you're graphing a function, I'm going to ask for 5 critical points. Critical points are minimums, maximums, and x-intercepts. For this function, we have one minimum here at the bottom of the graph, or 270 degrees, comma, -1. We have one maximum here at the top of the graph, or 90 degrees, comma, +1. And then we have 3 x-intercepts, one of which is also a y-intercept. 0, 0, 180, 0, and 360, 0. This is all the key information for the sine function. The last thing that we need to list is the domain and range. The domain is all input values, and for a sine function, since it's never undefined on the unit circle, the domain is all real numbers, which we will notate as -infinity to +infinity. The range is the list of all output values. Sine does have restrictions on the range. What's the lowest value obtained by the sine function? The answer is -1. Notice we switched to a bracket because unlike infinity and infinity, the sine function actually reaches the value -1, which means -1 is included in our domain. On the opposite end, what's the highest y value that sine reaches? We see that's +1. And so we complete our range as -1 to +1. Take a picture of this. This would be considered formulaic. This is something that is always true for the sine function. Let's do this again, but instead of graphing in terms of degrees, I'd like you to graph sine as a radian. And we're going to be using our calculator for part of this graph because we want to be able to graph both by hand and by using technology. You'll note that when you're using your calculator, your mode must be in radians. At this point, I'm going to assume that you've graphed functions using your graphing calculator before, but I'm still going to go over all of the buttons and the features that we want to use in our calculator. To start a graph, we push y equals. And once we've pushed y equals, we want to input our function. In this example, we're still going to graph sine of x. Double check that your mode is in radians. Mine is, as you can see. And then we're going to set our zoom or our window. Now there's 2 ways to set this. You can either press zoom, and there is a Z trig available for when you're using trigonometric settings, or you can set your window where x goes, in this case I'm going to say 0 to 2 pi, and y goes -2 to 2. Now we just talked about the range of y being -1 to 1. However, I like to see the entire graph and not have it cut off by the edge of the window screen, so I always overshoot my range. Here you have an option of changing your x scale from 1 to a more even output. We know that we labeled the last graph with 15 degrees, and so if we wanted to, we could scale our x's to be pi over 12. That says 13 over 12, which is the equivalent of scaling at 15 degrees. Let's take a peek at what the graph looks like. And there we have our sine graph. Now on an assessment, you are going to be asked to label your critical values exactly, which means the calculator is a great tool to get an overall image of what the graph looks like, but not a great tool if you're expected to label the points. I can't tell specifically where these values are unless I'm already familiar with the sine curve. One option is to go to the table menu by pressing second graph. This will give you a better idea of the points. For example, I know 0, 0 is an exact point. But again, we're seeing a bunch of decimals which are not considered exact. There is an expectation that you will be labeling your pictures with exact values, which means you need to be just as familiar graphing sine by hand as you are with the calculator. With that being said, we are labeling our x-axis in radians. So what are the critical values for sine? I know 0, 0. I know that sine peaks at 1 and peaks at -1. When does sine equal 1? You may have thought 90 degrees, but we want to relabel this graph in radians. What's 90 degrees in radians? The answer, pi halves. Again, sine hits 0 halfway around the unit circle. That angle is pi. And sine hits -1 down at 270 degrees, or better known as 3 pi over 2. Finally, sine is back to 0 by 2 pi. Generally, when graphing a trig function, we are going to be using the radian mode, not degree mode, although our first example was in degrees to gain familiarity. Let's take a look at the cosine function. This time, when we construct the cosine function, we're going to do it entirely in radians. Let's start a table where x is the domain in radians and y is all of the cosine values. Restart in quadrant 1 where the angles are 0, pi 6, pi fourths, pi thirds, pi halves, and since I have room, let's venture into the second quadrant at 2 pi thirds. What are all of the unit circle values for this domain? At 0, cosine is 1. At pi 6, cosine is rad 3 over 2. At pi fourths, cosine is rad 2 over 2. At pi thirds, it's 1/2. At pi halves, cosine reaches 0. What's cosine at 2 pi thirds? The first cosine value in quadrant 2 is negative, -1/2. Now sine didn't reach the negatives until quadrant 3, so we should see a difference between our graph of cosine and our graph of sine. Let's label from 1 to -1, from 0 to 2 pi. The halfway mark is pi, the quarter mark is pi halves, the third quarter mark is 3 pi halves. Right here we have pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. Now 30 degrees, or pi 6, is closer to pi fourths, and so I like to put these tick marks here to accurately graph my angles. Instead of starting at 0, 0 like sine, cosine starts at 0, 1. By pi 6, it's rad 3 over 2, and if you remember from sine, this value is still approximately 0.9, approximately 0.7, and exactly 0.5. Realized I didn't label all of my y-axis. There we go. So at pi 6, we need to be about 0.9. At pi fourths, we need to be about 0.7. By pi thirds, we're exactly at a half. And by pi halves, we've hit 0. Connect your dots in a continuous curve. I do have the first value into quadrant 2, which is 2 pi thirds, comma, negative 0.5. And now I'm going to start over and complete the cosine curve. And there we have a complete cosine curve. Just like sine, cosine is a periodic function, meaning after completing one period, cosine will cycle back through the exact same values over its infinite domain. This is what one period of cosine looks like. Let's go over the key information for cosine the same way we went over the key information for sine. When listing the key information, we want to know the critical values, the domain, and the range. So let's go over the minimum, the maximum, the x-intercepts, the domain, and the range for cosine. Starting with the minimum. The minimum for cosine is achieved in the middle of its rotation at pi, comma, negative 1. Cosine has two maximums, its initial value, 0, comma 1, and its ending value, 2 pi, comma 1. Cosine has two x-intercepts in its first revolution, pi halves, comma 0, and 3 pi halves, comma 0. And its domain, just like sine, is infinite, meaning all real numbers can be input into the cosine function. However, its range is restricted in the same way that sine's range is. Cosine will only achieve values from negative 1 to positive 1. Take a picture. This is considered formulaic knowledge of cosine. Let's begin graphing sine and cosine with shifts common to functions. Before we get specific to trigonometry, let's talk about some typical shifts that we see when graphing a function in generic terms. When given a function, f of x, there are a few things that we can do. We can stretch or compress the function by multiplying it by a factor. We can shift the function vertically by adding or subtracting a value to the output. We can shift a function horizontally by adding or subtracting a value to the input. And we can flip a function vertically by making it negative. All of these shifts can be applied to trigonometric functions, but be aware any shifts to the domain must be considered in terms of a periodic function from 0 to 360 degrees, not from our standard 0 to 10 that we're used to. So we're going to go over how each of these different shifts apply to trigonometric functions. Let's go over the formula of a trigonometric function. F of x equals sine A, B, C, and D. Each of these variables represents one of the four shifts that we described previously when referring to generic functions. What do these mean in terms of trigonometric functions? Well, A, formerly known as a stretch or compress, will now be referred to as the amplitude of the function. This determines how high up and how low down the function will range. B is referred to as the frequency of the function. This will tell us how many revolutions or periods of a function we can fit within the standard 360 or 2 pi radians. The frequency of a function can be used to calculate the period of the function by taking 2 pi divided by b. Next, we have what was previously known as a horizontal shift and what will now be referred to as the phase shift. When dealing with phase shift, you have to reference your period in order to shift your function an accurate amount. So the phase shift is actually going to be C over B, which will allow us to think of it in the same terms of our period. The last value is the vertical shift, and even in trig functions, it's still referred to as a vertical shift. Take a screenshot of this or copy down this slide because this is the information that we're going to reference as we graph functions with various amplitudes, periods, phase shifts, and vertical shifts. Now, in our rubric for our class, a student who approaches this standard will be able to graph functions that include both amplitude and frequency, but may not necessarily understand phase shift and vertical shift. In order to meet this objective, you must be able to sketch, both by hand and with technology, a periodic function involving all four types of transformations. If you want to exceed, we'll need to be able to graph trig functions and their reciprocals and use them to solve application problems. So for the rest of the notes, we're just going to graph a variety of trigonometric functions using a variety of transformations. Let's start with something simple. For our first example, we're going to graph f of x equals 4 sine x. This is the type of function we should be able to graph with or without our calculator, but for this example, let's go ahead and do it using both. Since we have calculators as tools, it should be expected that we use our calculator regularly in order to see what the graph looks like. Using my same settings from before, if I simply change this to say 4 sine of x, what's going to be different about this graph than the original sine graph that we graphed before? Let's take a look. You may or may not be able to see my screen, but if you also graph this, you'll notice that the curve goes off the screen. We no longer see the maximum or minimum values. That's because 4 is the new amplitude of the function. My function will now go up to positive 4 and down to negative 4. So let's change our window. I like to overshoot, and so instead of 4, I'm going to say negative 5 for the y min and positive 5 for the y max. And now I can see the entire curve. Let's choose a scale on our y-axis that allows us to graph this. 1, 2, 3, 4, 1, 2, 3, 4. Here's 4 and negative 4. Our first graphs were very specific. I made sure to graph every point along the curve. From now on, I'm only going to be using the 5 critical points for both sine and cosine in order to construct my graph. In terms of sine, those critical points are at 0, 0, pi 0, 2 pi 0, the maximum, which will always reach our full amplitude at pi halves, and the minimum, which will reach our lowest amplitude at 3 pi halves. Connect the dots in a continuous curve. Well, as continuous as you can, and you've officially graphed a new sine function. Based on the amplitude being 4, what has changed about the key features of this graph? Well, let's go back through them. The minimum, or the maximum, is now pi halves, comma 4. The minimum is now 3 pi halves, comma negative 4. The x-intercepts have all stayed the same. The domain is still all real numbers, but the range is now negative 4 to positive 4. Amplitude affects the range, the minimum, and the maximum. Let's graph another function. F of x equals negative 2 cosine x. Using a scale of 2 pi, what's going to change about this function from the original cosine graph? Well, now we have an amplitude of 2, and we're also going to flip our function because of the negative out in front. Get an idea of what this graph is going to look like by using your graphing calculator. In the function, we'll put y equals negative 2 cosine x. I'm going to use the same scale as last time and just modify if necessary. Since our amplitude is only 2, I know that the window setting from before that went up to 5 and down to 5 was going to show the full cosine curve. What's different about this curve from the original is that it's now been vertically flipped. Originally, cosine started at 0, 1, went down and back up. Now it's starting at 0, negative 1, going up and back down. Let's graph this using exact points. 1, 2, 3, 4. 1, 2, 3, 4. The first point on the cosine curve is at the minimum amplitude because we have a negative 2. We're going to go to 0, negative 2. What doesn't change about cosine are some of the critical features, like the x-intercepts being at pi halves and 3 pi halves. Now, originally, cosine had a minimum at pi, but because it's been flipped vertically, we now have a maximum at pi. Originally, cosine had a maximum at 2 pi, but because it's been flipped vertically, we now have a minimum at 2 pi. Connect your dots in as continuous a curve as you can. What of the key features has been changed by switching the amplitude of cosine to negative 2? The x-intercepts are still at pi halves and 3 pi halves, but now our maximum is pi 2. Our minimums are 0, negative 2, and 2 pi, negative 2, and our range is negative 2 to 2. We've now completed 2 examples involving only a shift in amplitude. Let's take a look at what happens when we change the period of our graphs. For our next example, let's look at a function that has a phase shift. F of x equals cosine 2x. What we know from our examples of the different variables, 2 is b, which is also known as frequency. Now there are two ways to interpret that the frequency is 2. In your mind, you can imagine that 2 periods of the cosine function will fit in 1 revolution, or 2 pi. Or you can use b to calculate that the period is pi. Earlier in this lesson, we wrote the formula for period as p equals 2 pi over b. Knowing that b is 2 means that the period is equal to 2 pi over 2, hence the period being pi. How does all of this relate to a graph? In order to see, we're going to need to graph this function. Setting our same scale that we've used in previous examples, we're going to label our graph from 1 to -1 and from 0 to 2 pi. In the middle we have pi, pi halves, 3 pi halves. With a frequency of 2, rather than fitting one cosine curve from 0 to 2 pi, I need to fit 2 cosine curves from 0 to 2 pi. To graph this change, I'm actually going to graph both the original cosine and our graph. So the original cosine starts at the amplitude, has an x-intercept at pi halves, a minimum at pi, the next x-intercept at 3 pi halves, and a maximum at 2 pi. How can I adjust this so that the period is only pi? In order to make this happen, I'm going to need to start in the same spot and end at the full period of pi. That means the minimum, which occurs in the middle of the cosine graph, now needs to occur in the middle of 0 and pi. The middle of 0 and pi is pi halves, so we will have a minimum at pi halves. In between, we'll have our x-intercepts, so I'm just going to mark those, and again, draw as continuous a curve as I can manage. Now, generally, we want to graph the full frequency, so we're going to repeat this process, starting at pi and ending at 2 pi, minimum in the middle, and x-intercepts in between. And now you can see I've managed to fit a frequency of 2 curves, each with a period of pi. Let's try it again, but this time with a smaller frequency. For our next example, we're going to graph f of x equals 3 sine x over 3. I'm doing 2 transformations in this example, and I want to identify both transformations. A, or the amplitude, is now equal to 3. This will affect my minimum and my maximum. I also have that the frequency in this example is 1/3. With a frequency of 1/3, that means I can expect to see 1/3 of a curve from 0 to 2 pi. Or I can calculate the period as 2 pi over 1/3, which when I type into my calculator, I get 6 pi. With this in mind, let's sketch this graph. An amplitude of 3 means I'm going to need to go 1, 2, 3 in each direction. Knowing that my period is 6 pi, having my graph only extend to 2 pi isn't going to be enough to see the complete picture. So this time I'm going to put 6 pi on the end. That makes this 3 pi over 2, and in between 3 pi and 6 pi is 9 pi over 2. Sine originates at the origin and ends at its full period. It has an x-intercept in the middle. And because this one is positive, I don't need to worry about flipping it. I'm going to reach my full positive amplitude, return to 0, a full negative amplitude, and return to 0. That's my complete sine curve with 6 pi as one period. Let's compare that with our calculator. If I go to y equals and change the equation to be 2 sine x over 3 and graph it, what am I going to see? I'm going to see 1/3 of the sine curve. Why? Because my window is still set to only display 2 pi. If I want to see the entire curve, I'm going to need to adjust my window settings to 6 pi, which is 1 full period. With the new settings, you can see the entire sine curve matches my curve over here. To practice graphing functions using period and amplitude shifts, please draw the following scale on an entire sheet of paper. Once you've completed this scale, I'd recommend drawing these 4 functions. On the same graph. You can color code them, you can use labeling techniques. As you graph each one, I want you to find the following information. What is the amplitude, the frequency, the period, the maximum, the minimum, the x-intercepts, the domain, and the range. This is the full expectation when you graph. Now these points can all be labeled directly on the graph or can be listed separately to the side. Pause the video here, graph the following functions, and when you're ready, replay the video to see the solution for each. Quick summary of what we learned in the first lesson for Objective 4, Graphing Trigonometric Functions. Sine and cosine are periodic functions ranging from -1 to 1. Amplitude affects the range of the function. Period is affected by the frequency with the relation frequency or period equals 2 pi over the frequency. We've also learned that the parent function for sine starts at 0, 0 and ends at 2 pi 0. It maximizes at pi halves, comma 1, and minimizes at negative pi, or 3 pi halves, negative 1. Cosine starts at 0, 1 and ends at 2 pi 1, maximizes at the start and end, and minimizes at pi negative 1. From these parent functions, we can include an amplitude shift and a phase shift with the following changes. Instead of 1, use the amplitude. Instead of saying 2 pi, think instead of the period, whatever the period may be. If the standard period is 2 pi, pi is half the period. Pi halves marks the quarter mark, and 3 pi halves is the 3/4 mark. With this understanding of key features of sine and cosine, you can graph any function using any amplitude and any phase shift. This concludes the first part of the lesson. Keep in mind what we've done here will only bring you to approaches on the rubric for Objective 4. All we've done is amplitude and period shift so far.